I'd like to talk about our presenter, Dr. Craig DeForest. Um, you know, folks, the first time you look at what he does, you might say it's a lot of syllables that I'm not quite used to pronouncing, but he can say heliophysicist, and it all comes off the tongue trippingly well, right? Pretty much like you would in maybe a Shakespearean play. Southwest Research Institute, based in San Antonio.
No, he is in Colorado.
He's actually in Colorado. Okay, very cool.
Thank you.
Good. BA in Reed College and Stanford University. An interesting thing, going from a BA, I guess that was in physics probably, to the PhD in Stanford. Now look at these interests. Formation of solar corona and the solar wind. Imaging science. Magnetohydrodynamics modeling, another one of those words that only Shakespearean actors should be forced to say. Modeling the sun's magnetosphere and how it flows. Open source scientific computing. I'd actually like to talk with him about this because I'm thinking he's talking about basically managing high performance computing arrays, supercomputers, if you will. And intuitively, I think that would be what it might be. He's the head of the Department of Solar and Heliospheric Physics at the Southwest Research Institute, a former chair of the American Astronomical Society's Solar Physics Division, and the principal investigator of the PUNCH mission. That's one of the main things he's going to talk about tonight. Without further ado, I'm going to turn it.
I've been practicing since Stanford days.
Okay. So, Craig, we have one of your old colleagues in here.
Yeah, I was just saying, hi,
Joe
Craig.
Dellinger.
I've known him since Stanford days in the 1980s. We were both members of an eating club called Breakers, which was eating club was just a co-op where you took turns cooking and cleaning, and so there was no hired people there. Everybody just did everything for themselves, but it was a great social thing. It no longer exists. The eating clubs at Stanford were killed off by the internet and everybody working from home. It lasted a century. It was a great institution, and that's where I know Craig from. And it was a great institution for meeting people who are in all sorts of different departments. So that's why a geophysicist would know a physicist.
You remain
But anyway,
an inspiration to everyone who knows you, Joe.
Yes, we all definitely know Mr. Joe or Dr. Joe. That's right. One of the things we're doing here, Craig, is actually getting a volume check on you right now. So if you can go ahead and say a few words, maybe.
How's this sound? A few words.
Okay, we're trying to crank up the volume a little bit.
Hippopotamus, Chalcedony, Apophanax, Velleity.
Okay, all right. Those are some very good words right there. Anyway, so what I want to do is I'm going to sit down and pass the baton to you, and please make us much more aware of the PUNCH mission and basically the things that we're hoping to achieve from it.
All right, let's see if I can share my screen here. Let's see, we don't want the whole screen because that will shrink the slides. Let's try one more time here. Window. Here we go. All right, can you guys see my slides?
We do.
Excellent.
We do, Craig.
Woohoo. All right, so I'm Craig DeForest. I still feel like that kid who was hanging out with Joe back in the 1990s. I like to talk about the fact that we used to do things in the 20th century because that sounds cool here in the 21st. I'm going to talk about imaging nearly nothing at all. I was here at this club about 5 years ago. Some of you may remember that. I had embarrassing pictures of Joe at that time. I didn't bring them back just because there's a lot to talk about, because now instead of talking about this upcoming mission that's going to be cool, I can show you this cool mission. So we're going to start out with why study the sun anyway. Many of you know solar physics, or at least stellar physics, at the nutshell level, but it's worth revisiting and talk about solar physics as something unique, which is astrophysics of our home here in space. I'll tell you a little bit about what PUNCH is. That's this mission that you just heard about. And then I'll show you some cool baby pictures and some data, which are unlike, I guarantee, anything you have ever seen before. So If you start to fall asleep, you'll want to wake up about halfway through and look at these things. So why study the sun anyway? That was a question that was asked of my advisor in 1991. I studied under a fellow who learned how to make these amazing UV telescopes, ultraviolet telescopes, that let us see the corona in a completely then new way. He talked about them for an hour to the material science department and how amazing these materials were that can reflect extreme ultraviolet. And at the end, that was the first question. Why study the sun anyway? Isn't it just a big ball of gas in the sky? Well, we all know that it's a little more than that, but it's worth revisiting. So here's our sun, cutaway view. Most of you have probably seen one of these because you're an astronomy club. The sun, of course, is not very, the metabolism of the sun is not very great. It produces about 10,000 times less heat on a per kilogram basis than you do. So you or your favorite mammal produce 10,000 times more heat on a kilogram for kilogram basis than the sun does. It's just the sun is very, very large. So the only place where fusion really happens is down in the core. There's a zone called the radiative zone that doesn't convect, where heat is transferred outward through the material by radiation and re-radiation. There's a convective zone where it turns over just like water on the boil on your stove. Hot material comes up from below, rises to the surface, spreads out, and sinks. And that's a very vigorous process you'll see in a moment. The thing you see if you look at the sun in the sky is the photosphere. That's the first layer that is opaque. And then there's some layers above that, something called the chromosphere, that's hotter than the photosphere, weirdly, the transition region, and then the corona, which is many times hotter than the surface. This is sort of the rough anatomy of a star. And of course, if you have an H-alpha filter in your telescope, you've probably seen solar prominences with your own eyes. This is what the surface of the sun looks like through a 1 meter diffraction limited telescope. There's granules going on. Those are convective cells. Texas is added for scale. We think of Texas as a big place, but it's very small compared to the sun. So those granules are convection cells up near the top of the image. Those turn over in about 5 minutes. So the flows are several kilometers per second. That's comparable to orbital velocities around the Earth. It's a very vigorous process, to put it mildly. There's about 1 million of those all over the surface of the sun all the time, day and night. It's a very loud and turbulent place. This dark thing to the lower left of Texas here is a sunspot. It's about the size of the Earth. And that's a region where the sun is magnetized. I don't have time to talk about the solar dynamo here, but it's the motions of the material that induce electric currents and magnetic fields in the star itself. Those are concentrated by the convective action and by winding motions in the interior. And they emerge to form sunspots. So in the sunspot, it's dark because the magnetic field is strong enough to inhibit that lateral motion you see up in the granules. And so the convection cells can't turn over, and so no new material is brought up from below. And it cools down from about 6,000 Kelvin to about 4,000. So it looks dark compared to the sun. And the fibrils here are where the magnetic field is tipped over and it's distorting the granulation. This field of view is about 8,000 miles across. I like metric, so 13 megameters across. The sun itself is about 1.4 gigameters across. That's about 870,000 miles. And you can see the Earth to scale there on top with the same sunspot that we were just looking at. So that is the sun. It looks sort of uninteresting at this scale in white light, but of course there's a lot more going on. One of the things that you can do is nowadays, for the last probably 35 years or so, is look at the sun routinely in magnetic field. As the sun rotates about once a month, the magnetic field evolves in a pretty amazing way. And so this is a movie of the magnetic field component that pierces the surface. White is north poles, black is south poles. You can see there's just a lot going on with knots of field erupting from the interior of the star. That shapes everything in our solar system. It shapes the atmosphere of the sun. It heats the corona to over 100 times the temperature of the surface. And it shapes the very interplanetary space where we live. So just to give you a better view of that, if you digitally derotate the rotating sun, you can actually see that convective action on the surface. These are larger scale convective cells called supergranules that are moving around all the time and pushing around the magnetic flux that's on the surface of the sun. So what I want you to imagine is magnetic field lines piercing the sun, coming out through the white spots and in through the dark spots. And they do things outside. On the inside, they're sort of pushed around by the material, but on the outside, they run the show. What does that look like? This is the solar corona, 1 million miles across, 1.6 gigameters. And what I want you to see here is the material is confined by magnetic field lines that are penetrating the surface. So I mentioned field lines come out through those white spots, in through the dark spots. And you can see that happening here because material is confined to follow the magnetic field. And so the shape of those magnetic loops is set by that pattern of north and south poles on the surface. What you're seeing here is material at 1 to 2 million degrees Celsius or Kelvin. So it is proportionally as much hotter than the surface of the sun as the surface of the sun is hotter than liquid helium. So it's quite a contrast, and it's good to remember that. This is what it looks like in white light. It's hard to see a show of hands when I'm sharing my screen, but how many of you have seen an eclipse? You saw the eclipse in 24? All right, cool. So a lot of people went right through Texas. This is the 23 eclipse that went through Australia just before. But when you see an eclipse like that, you're looking at the hottest thing you will ever see, right? I hope it's the hottest thing you will ever see at about 1 million degrees Kelvin. You're also seeing something we don't normally see, which is electrons, right? Right now, you and I are talking because we have harnessed electrons and electrical signals. They're all around us, right? They're powering the lights that are over your head. What do they look like? Well, they look like that. At least a lot of them look like that. Electrons in the solar corona that are free and divorced from any atom scatter sunlight. And what you're seeing there is the sunlight that's been scattered by them. Just like when you look at a blue sky, you're looking at sunlight that's been scattered by air molecules. What I want you to see here is, there's a lot more structure than you might think to the corona, even far above the surface. And if you're astute, you'll notice this is a color photograph, and you can see the chromosphere there with some beautiful prominences that were sticking up over the limb. Together with, down here, that spot is real. That's a piece of ejecta that left the sun, but it's still cool and still glowing in the hydrogen lines. Moving farther out, astrophysics of our home. This corona, this hot atmosphere of a star, is so hot, it's not gravitationally confined. It's only magnetically confined. And so out here, far from the surface of the star, 1 or 2 solar radii out, the magnetic field is no longer strong enough to hold the material in, and it streams outward, dragging magnetic field lines with it. That's why you see these radial lines everywhere. It's hard for the material to go sideways, but there's so much pressure from the heat, the high temperature of the material, that it streams out, dragging that magnetic field with it. So it remains laterally confined, even though radially it's escaping into space. So what that looks like farther from the sun. This is 25 gigameters, so almost a fifth of an AU away from the sun. That yellow disk shows the sun to scale. This is the deepest field image sequence of the corona that had ever been made to that date. And what I want you to see is that the structure goes all the way out. This is a time lapse of about 3 days worth of data. there's material flowing outward from the sun all the time in all directions, and those radial lines are real. Now, there's a radial filter applied here, so the drop off in brightness is sort of canceled out. It does drop off in brightness, and you would see stars here if the images weren't heavily processed. But you can see the material just constantly leaving. If we move farther out, this is another instrument called a heliospheric imager that looks at the outside of the corona. This is a white light camera. And again, the images are heavily processed to remove stray light, to remove the zodiacal light, and to remove stars. But when that happens, you can see the limits of those radial lines coming out of the sun. Pay no attention to that weird thing. That's Venus, and it looks weird because of the processing. We've averaged in time in a moving frame of reference, and so it makes Venus look really weird. But what you can see here is those radial lines coming out from the sun extend out to about 60 solar radii. That's sort of the middle of this field of view. And then they just sort of peter out. And what's happening there is the material that's streaming out from the sun becomes a sort of solar wind, streaks across the solar system all the time, fills the void between planets. And it is a fluid. It's so tenuous, nothing in the fluid ever hits anything else. No two atoms ever collide, but they exchange momentum through the electromagnetic field. So they act like a distributed fluid, just like the air around us does, even though it's made of molecules. In the air, it's molecular collisions that are exchanging the momentum. But out here, it's the electromagnetic field. But it still follows the same hydrodynamic rules. So what you can see here is stuff keeps flying out, but these straight lines break apart. It's reminiscent of the stream from a super soaker or a garden hose or something. And that's because it is, in fact, the same hydrodynamics that's at play here in your garden hose or super soaker and in this hydrodynamic system. So very exciting to be able to see that some time ago. This is a quiet day. This is a not so quiet day. That magnetic field that's entering the solar atmosphere builds up and becomes unstable sometimes and throws large clouds of ejecta out into interplanetary space. Those are called coronal mass ejections. And you can see they're quite complicated and quite large. They form something called space weather, which we'll talk about in a moment. So just to give you a sense of the scales involved, there's the sun. We're going to zoom out from it into some very wide fields of view. I'm about to show you data from a mission called Stereo that was far away from the Earth, looking back toward the Earth-Sun line. And the scales are so diverse that we had to go to polar coordinates. So that's the sun over on the right, and the edge of the sun, which is a circle, looks like a vertical line here. And then various other fields of view through the corona and out into the solar system. And because it was far away from the Sun-Earth line, we can see the Earth and Venus, which have been placed there. They're not to scale, but their placement is correct. So if we allow that to play, what you can see here is systems of magnetic flux form in the atmosphere of the sun. They get ejected, they cross the solar system right here, and we can trace them all the way out on this logarithmic scale and radius, all the way until they impact the Earth. This gauge is being driven by data from a mission called ACE that is right in front of the Earth in the center of that circle. And what I want you to see is that when this large bright cloud that's crossing the solar system right here impacts that, it sweeps over the Earth, and we actually see it in situ with a spacecraft that sampled that same cloud. So yes, in fact, star stuff from the surface, near the surface of our star, in fact, affects us directly here on Earth. It crosses the void and impacts our planet. That forms something called space weather, which I mentioned, which is sort of a relatively recent field of applied astrophysics that is important if you are a ham radio operator, or if you use a cell phone, or if you like to use gasoline that's gone through a long pipeline, or if you like to use electricity. And I think given where y'all live, you know something about what happens when the electricity grid fails. So these coronal mass ejections impact the Earth. They get deflected around our atmosphere by the Earth's magnetic field. Our magnetic field reacts and changes a little bit, and that changes any sufficiently long wire, including a transmission line or a pipe, into an electrical generator. And so it can, in fact, damage electrical grids. And right now, your power company is well aware of space weather because they manage the risk from CMEs and long distance power lines. All right, enough on that. Forgive me, I've been studying this stuff for 35 years, and this is a distillation of a lecture series I gave at a summer school a couple of years ago, boiled down to 56 minutes. So it may go fast in places. So PUNCH is a mission to image the solar wind routinely, and it unifies two different fields of physics. Solar physics on the left is summarized by this time-lapse movie through the LASCO coronagraph. We can actually see the time evolution of the corona. And we study large-scale features on and around the sun using remote sensing. But people have studied the solar wind mainly by flying spacecraft into it. And the spacecraft sample things like, here you've got plots of the velocity, density, temperature, and magnetic field versus time. And so you learn almost everything there is to know. There's much more to learn about the field or the stuff that hit the spacecraft and nothing else. So very clever people work very hard to look at what these things that I used to call confusograms and infer large-scale pictures like what you see at left. So right now we're at a weird time. We have a mission called Parker Solar Probe that is bringing in situ sampling in through the corona and actually taking scoops out of the corona and analyzing them as it flies through so we can get the ground truth of the physics that's going on there. PUNCH goes the other way. We're bringing that large-scale physics out into the solar system so that you can see how the solar wind evolves. I'm going to pick up the pace a little bit here. These are early PUNCH data. I'll tell you how they were collected shortly. This is data not from a space telescope. This is from a space context imager. That's what PUNCH really is. This field of view is 90 degrees across, and you can see Orion there for scale and various other constellations. We've suppressed the star field, excuse me, by about a factor of 30. There's the moon. It photobombs us every month. The sun is to scale in the very center there, and you can see various other planets, Jupiter and Mercury, moving around. Venus should be in the field of view somewhere, probably behind the sun. But I want you to see these large clouds of material spreading out from the sun and crossing the solar system. That's what we're here to image, these various tenuous glimmers of light that are scattered by electrons in interplanetary space. And these are the largest. Here's one coming right at us. We tracked that from the sun all the way until it impacted the Earth. So we'll come back to this in a minute. That's what we do. So how does PUNCH work? We photograph the solar wind itself from this faint sunlight that's reflected off of electrons in free space. But it is very faint. So this plot shows how bright various things are that you see in the sky. Up above here, this is the desert sky, a mountaintop sky during the day. This is fractions of the brightness of the solar photosphere. So a typical bright desert sky at noon is about 100,000 times fainter than the surface of the sun. At the top of a mountain here in Colorado on a clear day, it might be 1/1,000,000th of the brightness of the sun. That's in a radiance basis, right? So that's per solid angle on the sky. That's the intrinsic brightness, not the total intensity. During an eclipse, things come down to 10 to the -7 or 10 to the -8, and you can actually see the corona here. That's this green curve, and that's sort of what you see with the naked eye during an eclipse. The zodiacal light picks up here at about 1 degree from the sun. By 1 degree, it's 30 times brighter than the corona. And by 10 degrees, the zodiacal light is the brightest thing around, right? You can't see it from a city or even on a full moon in the desert, but you can sure see it on a new moon in the desert. But you have a hard time seeing this K corona because it's 100 times fainter than the zodiacal light. It's by 10 degrees, it's fainter than the galaxy. So this is the challenge we face. This is our field of view. We look from about 1.5 degrees from the sun out to a full 45 degrees from the sun. And we post-process the data to remove all these other light sources that are so much brighter. So when you're looking at a CME far from the sun in our data, you're looking at something that's 14 orders of magnitude fainter than sunlight. So, there it is. There's enough variation in brightness across our field of view. We had to have two kinds of instruments. So we have a coronagraph that's on the left. That's a sort of wide field quasi telescope that has an occulter in the front of it that blocks out sunlight so that we can look close to the sun. We have 3 wide field imagers. These are imaging cameras with a 45 degree field of view, or 40 degree really, 45 diagonally, that look off to the side of the sun. And they have an artificial horizon that's a comb of little metal edges that blocks out the sunlight, and then a very deep baffle structure that gets rid of moonlight and other kinds of glint. There are 3 of those because we had to keep them close to the ground so that we could downlink all our data. And when we did that, we discovered there was a giant planet in the way. So we can't see all the way around the Earth-Sun line at the same time with any one wide field imager. So we have 3 of them. They're spaced 120 degrees apart in orbit so that they're looking out in all directions. They're flying right now around the Earth, right over the sunrise-sunset line. And as a reminder, as astronomers, that sunset is not a time, sunset is a place. And so their orbit is designed to stay over that place. This is what our field of view looks like. This is simulated data from the beginning of the mission. They're flying right over that dawn dusk terminator. We have the narrow field imager field of view is that circular region in the middle. And then we have these 4 large squarish regions outside that are looking out. And you're looking at a computer simulation of a coronal mass ejection that we rendered just to get a sense of what Punch would see. This is our field of view as seen relative to some familiar objects. This is at the 2017 eclipse. There's the sun up in the sky eclipsed by the moon. And here's like some houses and things. The full field of view is 90 degrees across. You saw that. But just to give you a sense, right, I'll remind you, that means it goes from the horizon to the zenith. So the only place to display our data properly is on a planetarium. I apologize that I didn't have a virtual one with me. So we'll have to use the computer screen. I'm not going to talk too much about polarization. The P in Punch is for polarization, and we use that to measure the 3D position of objects. We're not quite doing that yet, but we will. The amount of polarization in a feature in the images tells us this scattering angle chi, where my cursor is, and that lets us solve this triangle with the sun and Punch and the object. We can do that in a semi-automated way, so we can actually produce 3D images. We're not quite there yet, but we will be. Why aren't we there yet? Well, I'll remind you of this plot. I'm going to give you a demo of what our data reduction looks like. This is a prototype using the stereo data, not Punch data, but which is more complicated. So we did this back in 2011 with data from stereo. This is the field of view from a heliospheric imager looking back toward the Earth. If you're astute, you can see Pisces in the upper left. Earth is in the middle on the left here, and there's a bright bar coming from it because Earth is so bright that it actually spills electrons across the detector chip. And over on the right is Venus. That's zodiacal light all around. You're looking at 2-hour exposures, and I want you to look at this brightness scale, 0 to 30. That's in counts or photons per pixel per second. And that's important because it's going to change as we go through. So what we're seeing here is the planets, which are too bright, and the stars, which are bright, and the zodiacal light. But that's not what we want to see. We want to get rid of those things. So the first thing we do is remove the minimum value of each pixel in the entire movie. The zodiacal light is approximately stationary in this frame of reference, so we get rid of it that way. Now, there's a lot more stars visible because we're going not 0 to 30, but 0 to 1 count per second. And you can start to see some scattered light around the planets. That's optical scattered light in the lenses. But you can also see that there's some motion here over on the right. There's some bottom to the top slow motion because the F corona or the zodiacal light isn't perfectly stationary. It moves a little bit in the sky. But you can also see some right to left motion. That is the solar wind. Okay, so now we want to get rid of the stars. We can use the same trick. We resample these images so that the stars are stationary, and then we can just take the minimum value of each pixel across the whole movie. When we do that, we get this. We're now at 0 to 0.1, so a factor of 300 inside the dynamic range of those original images. We've thrown away 99.7% of the light. Now you can see there's really something going on here, right to left. But there's the images are dominated still by leftovers from before. So we can try and fit each pixel with a cubic polynomial in time. If we do that and remove that cubic polynomial, we get this. Now you can see there's really some motion going on. There's still a lot left over, and it's about the same size as the signal we're still looking at. We're from 0 to 0.03 now on the dynamic range. So we're a factor of 1,000 inside the original dynamic range of these images. We can use a technique called Fourier filtering to look for things that move only. And when we do that, we get rid of essentially all those stationary artifacts. And now you can see the solar wind. This ghostly white cloud moving right to left is the solar wind. And this was the first time anyone had seen it in this way. So these images were what allowed us to see punch. But I showed you them because I want you to recognize that the post-processing is an important part of what we do. The instrument itself collects the photons, but it's the post-processing that really pulls the imaging information out of the data. So that's what we do. I'm going to show you some baby pictures from Punch. These are pictures of the hardware that we flew into space. The Punch spacecraft aren't very big. They're about 1 meter long. 2 people can lift one if they were on the ground, which they used to be. This is the coronagraph, and it's NIFI during integration. That is the aperture or the baffle tube and the occulter right at the front of it. Over here on the right, it now has the actual aperture installed, and it's being tested in a vacuum chamber at the Naval Research Laboratory. There's artificial sunlight being shown into it. And we tested it in vacuum because air itself, Rayleigh scattering and Mie scattering in the air in a typical laboratory is brighter than the stray light from these instruments. So putting them in a vacuum chamber lets you test the instrument without the room around. This is what it looked like all assembled and ready to go with some remove before flight elements on it just to lock everything in place. These are what the wide field imagers look like. That's closed, that's open. You can see that there's a solar baffle there on the front and then these really deep veins that absorb moonlight and prevent glint from getting down into the chamber. There's the chamber of a fully assembled WIFI and the aperture. These devices are pretty amazing. Light doesn't like to bend corners. And so this instrument sits right now, it's sitting in the eternal noontime of space with direct sunlight on the front of it. And that little aperture in the back is about 100 times darker than the darkest night on Earth. So it's pretty astonishing how well baffles work. This is a picture of one of the complete spacecraft next to a technician right after integration. You can see some umbilical cables coming out to power it. This is a picture of the team that had just assembled the spacecraft taken by the spacecraft. So you can recognize, if we go back, that's the same cone there in the picture. And I like to throw this up to show you the wide field imagers are not telescopes, right? They're capturing their immediate environment, which in this case happens to be a clean room, but now is our environment in space. This is what it looked like during testing. On the left, we had it mounted on a bracket to go into that vacuum chamber. On the right, this is a picture of the inside of the vacuum chamber taken through the instrument, and it's demonstrating 10 to the minus 16 rejection of stray light. I'm pretty thrilled about that. This is our optics. Since you're all astronomers, you have used Nagler eyepieces. One of the last things Al Nagler did was design the optics for the wide field imager. They're very similar to an eyepiece. They're used in reverse configuration. Instead of taking a real image from a telescope and making it virtual at infinity, we turned it around. So we have the virtual image in infinity coming in from the cosmos and being focused onto a real image plane. And they work every bit as well as you would expect from a Nagler design. They're really incredible. All these little annotations, by the way, are leftovers. I apparently didn't scrub well enough because I gave this lecture or some of these slides at a college. So I was tying it into their course catalog. This is one of the spacecraft undergoing shake testing. That table is, well, unless you have worked with some of Joe's amazing creations, it's the loudest thing you've probably ever seen. That's a half a megawatt stereo right there, designed to shake the living daylights out of a spacecraft to make sure it still works. We put them in a thermal vacuum chamber to make sure that they wouldn't cook or freeze in space. And this is the team that assembled them in front of 4 crates that we then shipped off to California to launch into space. This is what they looked like unpacked at Vandenberg a little over a year ago. This is what they looked like a couple of days after that when we bolted them to the sides of a carrier assembly that was then bolted onto a Falcon 9 rocket. That cone up above is a different mission that flew with us called SphereX, went in almost the same orbit. This is a very rare picture of the completely enclosed launch stack heading to the pad. It's rare because you're not allowed to take pictures on Vandenberg Space Force Base, which is where this was. But there's a train track that goes across the base, and one of the passengers in the train happened to snap a picture of our stuff as it went to the pad. So this was taken through the window of a train as it went by. Kind of neat coincidence. This is what the narrow field imager looked like about a day after that. Over, you might recognize Madagascar behind it. And over here on the right is the wide field imager. There were 2 others that left at the same time. They were spring ejected and traveled out at about 1 meter per second relative to each other. So it took about 90 days and they got a third of the way around the world. Pretty exciting. So you've already seen this movie, but this is what the data look like. And that's why there's that sort of propeller effect, is we're synchronizing 4 different spacecraft and trying to match their photometric signal to roughly 1 part in 10 to the minus 4. We didn't achieve that for this movie. It's about 1 part in 10 to the minus 3, which is pretty good, but still leaves a residual after we subtract all that other stuff. So we take 1 polarized image set every 4 minutes from the entire fleet. We're still refining the data on the ground, but we're putting it in the can and we're distributing it. You can download and take part in this process. This movie was very early in the mission. Right after we started running the science campaign, the sun obliged and gave us a coronal mass ejection coming straight at us, which is about to go now. Boom. Whoops, there it is. So it looks a little bit like the Romulan weapon in Star Trek, right? Because it's just a cloud coming right at you. All right, so we've gotten better. This is what I like to call our Grandeur of the Cosmos movie that we made back in October. We were quite a bit better at processing at that point, but on the other hand, we zoomed in a little more so that we could see the corona better. So the artifacts are still prominent, just because we go in until the artifacts start to get dominant. So what you're seeing here is our vicinity in space, right? That's Venus on the right. That's the moon going by. There's Mars and Mercury. And of course, that is a familiar comet, Lemon, coming through. And let's see, you can see streaks up here at the top. These streaks in the images, that's the Starlink satellite constellation. You'll see brightening toward the end of the movie. You'll see brightening over the North Pole. That is aurora. As we flew over the North Pole to take those northern-facing pictures, the cameras started picking up aurora from these CMEs that were coming out throughout the fall. So yeah, the aurora will start to come in a moment. And of course, what we're really here to see, oh, there's the galaxy, you know, putting in an appearance. What we're really here to see is these clouds of material coming out in all directions from the sun. Now watch the comet tail here, Lemon, as there's a CME that comes out, here we go, crosses the solar system and impacts the comet, and it will sweep the tail there. That's just a reminder that these clouds that we see aren't subtle. They affect everything in the solar system, including us and including, you know, passing comets. The middle data here is not from us. The narrow field imager is suffering from additional stray light coming in from the Earth. So we used a different coronagraph to give context here, but we're working on making the narrow field imager work. So hopefully we'll have that. These are some close-ups of comets. It turns out as a side effect of looking at everything in the inner solar system every 4 minutes, we see comets really well. So this is Comet Swan, which was discovered on the 11th of September last year. We looked in our data and saw that we had been tracking it since the beginning of August. We just hadn't noticed. This little sequence here is through a 4-way conjunction between Swan, Spica, which just went by on the right, Mars just above, and if you look down below on this track, you'll see Atlas, the interstellar comet, as it goes by right there. And we can actually see it quite well in co-added images, but I think it's neat that you can see it with almost the naked eye, just in these basic unsharp masked images. The data reduction has gotten a lot better since then, but I like showing it just because, or showing this older version of the data just to compare and see how much better we've gotten. Whoops. So this is a close-up of Lemon, just showing the tail reacting to the solar wind. You can see turbulence forming and a disconnection, just all kinds of amazing hydrodynamics happening here in our solar system that you wouldn't normally think of necessarily. You've undoubtedly seen Lemon through your own telescope, but you haven't tracked it continuously for months at a time because you're limited by being inside the atmosphere. Oosh. Man, I love that. So this is some processing that we had available as of about a month ago. This is the same interval in September and October. There's the moon coming through. And it gets fainter as it gets close to the sun, of course, because it's becoming a narrow crescent. All that sparkling that you're seeing is the same bleeding that you saw in the stereo movie, where electrons get spilled across the detector chip. But because we're orbiting the Earth and rotating, the detector chip is at different angles, and we're merging it all back together. So this was our very first attempt at starfield removal. We didn't do very well at it because we're supposed to be interpolating between daily starfield images, and something went wrong with the interpolation code. Fortunately, the stars are pretty stationary, so the fact that we're using a single starfield was sort of okay. We do better now. If you look over here on the left, you'll see Comet Swan, which was making its exit. And there goes the moon by it. But you can see these clouds of material sweeping across the solar system. I want to remind you, this is where we live in space, right? This is our home. That's Venus there, Mercury going around. If you watch the whole movie, you'll see it stop and turn around. This is going on all the time, all around us. We just can't see it because it's too faint most of the time. Moving on, we're now looking at polarized brightness. I like the polarized images because although the artifacts look a little bit more prominent, the contrast is better. So the polarized brightness images are good here's the same movie, but with a radial filter applied so that you can really see the structure and the turbulence evolving in this material, right? I will remind you, again, this is a 90-degree field of view. So you're looking at things that are huge on the sky. They're enormous. If they were bright enough or your eyes were sensitive enough, you would see these with the naked eye, no problem, right? They're as big as the Milky Way in the sky. And they're sweeping over us all the time. Just to prove that we can cook, this is April, and I want to show you, first of all, that we're doing better with the star field removal now. This is Comet Pan-STARRS in the upper right, coming in slowly. You'll see it come in more. That's Andromeda there. First time I saw Andromeda clearly was with Joe, actually, on the side of Mauna Kea. But there it is. We see it all the time now. That's the Pleiades coming in, and Taurus. There's the moon going by. We're a little better at removing it, but it still kind of photobombs us. Oh, let's go back. Watch this. Pan-STARRS gets hit by a CME. Look at that tail. Oh, yeah. So anyway, this is just more recent, and we're churning out data like this now. So I've been yammering at you for most of an hour. We make these data available to anyone. We make them available as processed as you want. You can get the bits straight out of the spacecraft if you like, and you can go through all the effort to reduce them and pull whatever you like out of them. Or you can grab the more refined stuff, which we're working on. These are all preliminary. We are on version 11, which we also call version 0K of the data. We're about to release version 0L, which is about an order of magnitude better in terms of stray light rejection. Sometime this summer, we'll release version 1, which meets our mission requirements. You can get all of this at our website. One of the things we're rolling out with L is daily movies, so you can just, at a glance, sort of see what the solar wind looks like today. The sun is really complex, really fascinating. I could yammer at you for months about it, and have to poor students who didn't know what they were getting into. And of course, the void between our planets is not empty. It's full of this fluid that's so tenuous, we think of it as hard vacuum, but in fact, it obeys the same equations as supersonic fluid flows here on Earth. And this is where we live, right? This is our solar system. We don't normally see it this way because the sun's in the middle. So we might take images after sunset or before dawn and splice them together, but we don't normally see the inner solar system in this way. But this is our home. Thanks for your attention.
Hey, Craig. Yeah, let's give him a hand, folks. So Craig, we have a few minutes for some questions, but before we take the questions, I want to just make a few comments on what you presented to us. I think you have really helped the sun become real to us. Seeing these movies, seeing the solar wind, visually. You've seen the different presentations you gave of the scale of the sun, the corona, the solar wind, where Earth and Venus are and stuff like that. It really helped us become connected with the sun. Anyway, for me, it's like I've never been connected before. I really want to thank you for what you've shown us here. Now, we do have a few minutes for questions. Who has the first? And before we take questions, just want to let you know what we've asked you to do is to accept the microphone, ask the question, then we'll pass it on to the next person with the question. So the first question comes from Bill Spazzeri.
Hopefully you can hear me. I have two questions, if you don't mind. One of them is who finances Punch, and who funds it? And also, am I correct? All the prominences are in the chromosphere. Is that correct?
Let's see. So the first is you do. Thank you. Every man, woman, and child in the U.S. contributed 50 cents to Punch over the course of its development, and I thank you for that. I hope to give you your money's worth.
It is funded by us, the people of the U.S.
That is correct.
Okay.
That's correct. And so this is a NASA project funded through the Explorers program, and it cost about $150 million to put together and fly. It turns out you have to spend that kind of money if you want to put something custom into space and have it work right the first time. So as space missions go, it's fairly inexpensive, although it's a lot larger than my salary.
Yeah.
The
and that's unfortunate. That's unfortunate. Okay.
I think you got a lot of bang for the buck there.
Yeah.
Thank you. The prominences, of course, are part of the chromosphere, but I wouldn't say they're in the chromosphere, right? Because they're suspended by the magnetic field above the layer that we normally think of as the chromosphere. You might say they're fingers of chromosphere that extend up into the corona.
Okay, thank you.
All right, very good. We have about time for 2 more questions. Who has the next question? Okay, Miguel.
Yes, I have a question about the cameras. I understand with the current technologies, CMOS cameras seems to be more advanced, at least on paper. I would like to understand what is the rationale for using CCD cameras for this specific application. Thank you.
You're welcome. We use CCDs because they are low noise and they are extraordinarily linear. We rely on the extraordinary linearity of the CCD. We only fill it to half full, fill the wells to half full. And so the photometric signal is linear to better than 0.1% in these cameras. And that's very important, partly because in order to measure the intensity of a star, we have to rely on being able to measure that intensity to within 10 to the minus 4 or so, whether the star be centered on a pixel or centered on the intersection of 4 pixels. And so in the one case, much more, you'll get a strong signal in 1 pixel, and in the other case, you get a weak signal spread across 4. In those 2 cases, we need to get the same number at the end. And so we need to know that the camera is extraordinarily linear. That's why we went with a CCD.
Okay, thank you.
Fantastic. Who has the next question? Robin?
I'll ask the last question.
Do we have any idea of what the solar wind consists of? We would expect to see helium and all the atoms up to iron, but do we have any breakdown of the way it normally looks?
Absolutely. That's part of that month of yammering that I talked about. The solar wind is made mostly of the material that the sun is made of. So it's largely protons with free electrons mixed in, but there are also helium nuclei and trace heavier ions. And the abundances are slightly different than the photosphere because there's some filtration that happens in the process that brings the ions out into the corona.
Very cool. Hari, I think you had a question.
Yes, I have a follow-up question to Robin. He asked half of my question already. So I have 2-part question. So what is the speed of these coronal mass ejections, the solar wind? And 2, you talked about the comet tail getting disrupted because of the solar wind. How does that mass interact? Because mostly these are massless particles for the most part. Is it because of the volume of things flowing through space? How do they actually interact with the tail? Like, do you mind shedding a little bit of light on that?
Absolutely. I'm sorry, I didn't hear the first part of the question, or I did, but it went right out the other ear. So I'll address the comet and then we can come back to that. With the comet, what you're seeing is the ion tail is being moved around. And so the ions are picked up by the solar wind. Individual gas molecules get ionized by ultraviolet light from the sun. And once they're ionized, they feel the local magnetic field. And so I mentioned the field lines are pulled around by the solar wind, which is a fancy way of saying there's electromagnetic induction happening. So when the wind sweeps over the comet tail, it sweeps magnetic field lines over the comet tail that induces currents in the local environment, and the comet tail responds to that.
Okay. No, and the first part of my question was the speed of the solar
Oh,
wind
right.
itself.
Speed of the CMEs. It takes between 1 and 4 days to get from the sun to the Earth, and it turns out that's between 4 and 1 million miles per hour in round numbers. Going back to metric, what is that? 300 to 1,000 kilometers a second.
Yeah. No, thank
I
you.
think we had 2 more questions. We got Jeff and we got Richard, and then after that, we'll need to take a break.
Yeah, you mentioned the intensive post-processing, and I do astrophotography, so I can kind of somewhat appreciate that. What software do you use to post-process? Is it you write your own, or do you use some kind of commercially available software?
We mostly wrote our own, and we use open source analysis software. That's one of my main interests, is to supply high power tools to individuals. So for 20 years, I worked on a language called Perl Data Language, which is still my first love as an analysis language. It's a vectorized language. There are several of them now, but it's in the family that started with APL back in the 1970s. Extraordinarily powerful and versatile, and free and open source. However, the writing's been on the wall for a long time that Python is sort of won the hearts and minds of generations now of CS students. So all of the punch software is custom written, but it is open source. It's in Python, and you can use it to analyze any image stream that you like. You can find it at our website.
Very cool. Richard?
One quick kind of relatively bizarre question, but this is all speaking about our own sun. What do you think the opportunity of doing this with another star nearby or other stars in the future? I know not obviously sending spacecraft there, but maybe there's another way to look at other stars. And how do you think that affects the entire galaxy when you multiply this kind of solar wind across all the stars in our galaxy?
Isn't that remarkable? One day we may very well image the corona of other stars. It requires a large space telescope. But if you do it in the extreme ultraviolet, the photons are smaller, right? So the diffraction limit can be very, very good. So it turns out an EUV imager that's just a meter or so across could probably image the corona of nearby stars. I'm very excited for that prospect. In terms of how the interstellar medium is affected, you know, this solar wind extends out around the sun and forms a bubble in space that we call the heliosphere. So heliospheric physics comes from that. There is a termination shock at the outer part. That's a density wall, if you will. It's a stationary shock where the solar wind slams into the interstellar medium. If you want to know what a termination shock looks like, just, you know, run water into your sink, right? You know, there will be a region at the base where the water from the flow is spreading out very fast, and then a wall of water will appear that's much slower. That is a shock in that two-dimensional hydrodynamic system. So this is a three-dimensional system, so it's not a circle, it's a sphere. And in fact, it's distorted because the medium is moving relative to us, or vice versa. But there's a large teardrop shape around us that's dominated by our solar wind. The interstellar medium has a different composition, and it's composed of a mix of more primordial star stuff, whatever was left over, and the remnants of stellar winds. So in places where stars are even more dense than they are here, I would expect that the interstellar medium would eventually basically be composed of the same material as the stellar winds.
Wow. Let's give Dr. DeForest another hand. Craig, this was a fantastic presentation. Thank you very much. If you want to hang around for the rest of our meeting, you're very free to do so. We're going to take about a 10-minute break now. We'll reconvene at 8:20.
Wonderful.
And the cowbell rings. Cluck, 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 cluck. Okay.
It's an honor and a pleasure to speak with you folks.
Absolutely. No, thank you. Thank you, Dr. Forrest. This is beautiful. This is brilliant. Thank you.